Good morning, all. Today we're going to be looking at truth tables. This is going to be an introduction to truth tables. And we're probably going to have two different videos for this. In this video, we're going to be starting with the basics. What is a truth table? What is it used for? And then we're going to use the truth table to define how our five operators work in philosophical logic. I should mention this ties with chapter 14 of the textbook for my current class of logic, chapter 14 of Herrick's Introduction to Logic. But every philosophical logic textbook has the same material, so it can be used for anything. And here I'm going to be using the standard traditional operator symbols, not necessarily Herrick's, who uses the ampersand for and. So a truth table is a way of understanding what a statement, what a well-formed formula in propositional logic means. And if you don't know what a well-formed formula is, check out my other video, the video I put out last week for this class on well-formed formulas, or chapter 12 in our book. Essentially, a well-formed formula is just, a grammatically correct statement in logic. And so like having the P by itself is a well-formed formula because the P or the Q represents just a single declarative statement. But also connecting it with operators in valid ways is going to be well-formed as well. And that can become quite long and complex. That's a topic for a different video, and we don't have time to get into that here. So anyway, the way to understand this, so whenever we're looking, let's just look at the and, for example, right here. We're basically asking, what does it mean for P and Q as a whole? What does that mean for it to be true? Like, what are the requirements for that? And the truth table will help us break this down, and then we can really see a concrete distinction between the different operators. So part of this video is going to be a review of these five operators as we go through it, but then also help us to understand what the truth table is doing. And then in the next video I do on truth tables, we can look at how to use truth tables to understand the validity of our four starting forms, which for us is going to be modus ponens, modus tollens, disjunctive syllogism, and hypothetical syllogism. And then even to show how we can prove an argument is valid or invalid using these truth tables. But for today, for this video, we're just going to be talking about defining operators. Okay, so here we have in these columns, this is column 1 here. In these columns, we're going to be simply looking at statements on their own. So what is, we're looking at P, we're looking at Q here. And this is going to be kind of like our starting bracket, kind of like our key. And then that will guide what's in these two columns, will guide how we understand what should go in the other columns. Okay, so kind of like a multiplication table, except that, well, it's for propositional logic. Okay, so I think the best way to just move forward is just to talk about what these operators do. And I'll just go one by one. So the and, remember that when we use the and operator, and this is basically true in normal and natural languages as well. When we say P and Q, for that to be true, P has to be true and Q has to be true. They both have to be true. And if either one is false, or if they're both false, then the sentence ends up being false. So for example, the example that I keep using is Springfield is the capital of Illinois and St. Paul is the capital of Minnesota. Take that as a single whole sentence. And that sentence, in order for it to be true, both the first part about Springfield being the capital of Illinois and the second part about St. Paul being the capital of Illinois, both of those have to be true in order for the sentence to be true, okay? Meanwhile, if one part is false, then the entire thing is false. So if I said instead, Chicago is the capital of Illinois, and St. Paul is the capital of Minnesota, that statement is false. Even though St. Paul is the capital of Minnesota. And it's because one part of that sentence, Chicago is the capital of Illinois, is false. Okay, so the way we're going to break this down is like this. In these two columns, we are essentially going to express every possible combination. Each row is a different possible combination of truth values for P and Q. Now, P can have two truth values, either true or false. And Q can have two truth values, either true or false, just like every other statement in logic, right? So with two possibilities of P and two possibilities for Q, that is 2 times 2, or 4 total combinations. And the way we'll express this is in this first column under P, we're going to have the first half be true, and the second half be false. And then in the second column, we're going to alternate true, false, true, false. So it's kind of like the wheels on a combination lock, where the ones place is spinning 10 times faster than the tens place, except here, this is binary, essentially, where the ones place is spinning twice as fast as the twos place. So this would be the, yeah. So it's either 1 or 0, 1 or 0. True, false, 1, 0, 1, 0. Okay, so on this first row then, this row represents when both P and Q are true. And what we're looking for in every blank spot on this chart, what we're looking for is, what is the truth value of P and Q? What is the truth value for this formula when P is true and Q is true? Now, again, the meaning of P and Q is that both P is true and Q is true. And so when P is true and Q is true, we are fulfilling that expectation or that condition. And so we can say that P and Q is true. However, since all of these other rows lack the truth in both parts of the statement, it's true in one part and false in another, it's going to be false in the other 3 columns. So this pattern here, true, false, 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 this is what an and statement is always going to look like. And when I say that, I don't necessarily mean that first comes true and then second, third, and fourth comes false. That's going to be dependent upon what order these rows are in. But what we see here is that when P is true and Q is false, that gives us a false statement. When P is false and Q is true, that gives us a false statement. When they're both false, that gives us a false statement. Okay. So that's the basics. And the and is, I think, probably, well, just about the simplest one to understand of these. Next up, let's look at P or Q. Now remember the word or for us. There are 2 different ways to understand the word or, exclusive or and inclusive or. The exclusive or would mean something like either P is true or Q is true, but not at the same time. Or I should say, I should take out the time part because it's not really pertinent to this kind of logic. But either P is true or Q is true, and not both. Okay. That's the exclusive version of or, and that's what we're not using. I made a video about this as well, the 2 different uses of the word or, and we will be using the inclusive version. So the inclusive version of the word or means that at least one of them has to be true, but they could both be true as well. It's kind of like when the example that I've used when you go to a rated R movie or you go to a bar and they card you. They're like, well, you have to be of a certain age, so we need to see some form of ID, either a driver's license or a passport. They're using the inclusive version of the word or there, even if they say either or. Like that, the either or doesn't actually dictate that it has to be exclusive. And when I say that the bartender or the bouncer or the person at the ticket agent in the movie theater, when I say they're using the inclusive version of the word or, that means that if you gave them multiple kinds of ID, they're not going to turn you away. They're going to be like, well, that was unnecessary, but sure, you totally passed this. You've totally proven your age in this for our sake. So what does that mean here? When we go back to this, P or Q, we see here that P is true and Q is true. So remember, the condition for P or Q is that at least one of them must be true. Well, at least one of them is true. Both of them are true. Therefore, we're going to put true here. Row 2, P is true and Q is false. Again, it fulfills the condition of at least one of them being true. So this is true as well. Next, P is false, Q is true. Again, we have at least one of them being true, so this is true. And finally, P is false and Q is false. Now, for the first time on this column, for the or, we see the condition not being fulfilled. Neither one of them is true, and therefore we would consider P or Q to be false when both P and Q are false. Simple as that. Okay. Next, we have the not. Now, the not symbol, again, this just reverses the truth value. And this is going to become a little redundant for us. We don't need 4 rows since there's only P in this particular formula. And you might recall that the not is what we call a monadic operator. It only attaches to one statement at a time, unlike all the other ones. Because it only connects to one, we only need to look at the P. We don't need to look at the P and Q. Not P, well, what is the truth value of not P? When P is true, it's false. It's simply the opposite truth value. And this is the redundancy because we've repeated P twice. We're going to repeat it twice here. False, false, true, true. Okay. Next up, we have the if then. This is, I think, for many people, the most confusing, the most counterintuitive. And remember the way this works. I'm just going to remind us about how the if then works. When we say if P, then Q, this only really hooks into the logic of a statement if we also know that P is true or Q is false. If we know that P is true, then that forces Q to be true. That's modus ponens. If we know that Q is false, that forces P to be false, not P. That's modus tollens. However, suppose we learn that P is false. That does not lead to Q being false. We can't tell anything because this statement isn't saying when P is, it's not saying that P and Q have the same truth value. It's not saying that if P is false, then Q is false. It's only saying if P is true, then Q is true. So if P is true, Q is forced to be true. And if Q is false, then P is forced to be false because if P were true, Q would be true, violating the statement, okay? So we want to think about this, and what we're going to realize is that in some cases, like for example, if P is false, we don't know if Q is going to be true or false. And so we're going to have a sort of like an unknown. Is the statement, so like what I mean by this is, given this statement, if P is true, then Q is true, and P is true. That forces Q to be true. So in this case, P is true, and Q is true. And the statement keeps its integrity. So we're going to say that the statement as a whole is true. Down here, when Q is false, and it forces P to be false, P is false and Q is false. Again, this is working within the integrity of the statement. So even when they're both false, the statement can be true. This is modus ponens and modus tollens. Here, not P. If P, then Q. What do we know about Q in this case? We don't know anything because the conditional doesn't hold. So when P is false, what do we know about Q? We don't know anything. But it doesn't matter what it ends up being. Regardless of what it is, it doesn't violate the integrity of the statement. So if P is false and Q, it doesn't matter what Q is, we're going to say that the integrity of the statement has not been broken. So whether Q is true or false, it doesn't matter. Finally, what does matter is this. Suppose if P, then Q, we assert P again, but then it turns out that Q is false. This is a direct violation of the statement, and this is the only pattern that is a direct violation of the statement. When P is true and Q is false, this cannot be true. We have broken what that statement means. In some cases, so to review, in some cases, we are upholding. It's like we're confirming the truth of the statement. If we have declared that if P is true, then Q is true, and then P is true, and we find out that Q is true, that upholds the integrity of the statement. Likewise, if Q is false and it forces P to be false, that upholds the integrity of the statement. If we find out that P is false, we don't learn anything about Q. The integrity of the statement hasn't been confirmed, but it hasn't been denied either. And this is, I think, is the most confusing part of this. When we don't directly violate the truth value of the conditional, we're going to treat it as true. The integrity has not been violated. It's only in this last one, when P is true and Q is false, that we treat the conditional as false. Okay, so let's go back here. And what we see here, when P is true and Q is true, that's like a working modus ponens. This is true. Line 2, P is true and Q is false. That's this. This is where, line 2 is where the conditional statement breaks. It's where, if we say, so like if someone has declared if P, then Q, and whatever they're talking about, but then we find out P is true and Q is false, the statement ends up being false. Down here, when P is false, that's like over here, when we find out P is false, and it doesn't matter what Q is. So regardless of whether, so here P is false on rows 3 and 4, P is false. Sometimes Q is true, sometimes Q is false, but in neither case is the integrity of the statement violated. So the conditional row looks different than the other ones do. This is true, false, true, true. So before, like comparing this to the and the or, the and, it always comes in like 3 and 1 for the and, or, and the conditional. For the and, we have 1 true when both are true, followed by 3 falses. And it's row 1 is the exceptional one, is the one that is different than the rest. In the or, we get 3 trues and 1 false. For the or, it's down here when both are false that stands out, that is the exception for the or column. The not is just half and half, pretty ordinary, pretty plain. The conditional is also 3 and 1, except here it is row 2 that is sort of stands out. And that's the exceptional one. So this column, I encourage you, I don't know if this explanation made sense, but I encourage you to give it some serious thought and to take a look at the book and spend some time studying this. Like this, it might be the most confusing part of this, but it's also the part of this whole table that to understand this row perfectly clearly is going to provide the greatest boon for us in understanding what logic is as a whole. Because that if-then statement is the heart of what logic is, more so than the and, more so than the or, because the if-then statement is behind everything. And to understand why this ends up being false, but the others are treated as true, kind of helps to unlock the secret of what logic is. And not just for philosophy, but for every application of logic, which is essentially in every corner of our lives. It's like art, way, totally different topic. Sort of, but beyond truth tables for now. Okay, finally, the logical equivalence. Remember, logical equivalence simply is saying that the two statements have identical truth values. So this one's actually maybe the easiest one. All we do to figure out the truth value for P being logically equivalent to Q, all we have to do is ask back to these original columns, do they have the same truth value? Do P and Q have the same truth value when P is true and Q is true? Obviously, yes. Therefore, it's true. Do P and Q have the same truth value when P is true and Q is false? No, clearly not. Do they have the same truth value when P is false and Q is true? No. Notice how, before we do this last one, notice how so far it's identical to the and. True, false, false. But now, this is the big difference here, that when P is false and Q is false, as we have here on the last row, now it's true on the last row, because false is the same as false. And that's the last one. By the way, just to kind of fill in this concept a little bit more, let me erase some of this. Better way to do this. Another way to express the logical equivalence is that we might consider this a complex symbol because there are ways to break it down into the other symbols. And the way we would do this is if P, then Q. If P is true, then Q is true. And if Q is true, then P is true. Or we can do it in a totally different way, that either P and Q are true, or P and Q are false. This symbol can be broken down into either of these ways, and the symbol is not actually necessary. But one reason, in logic, we try to keep the number of symbols we have to a minimum. But this is like the exception. This is one that's an exception. There's another exception, and I'll show it to you. But this is an exception because of how many different ways or how many different parts a breakdown would require. So this does help save us time a lot. By the way, like almost all of these symbols can be broken down further. For example, you don't have to know this right now. We will find, you don't have to know this right now either, but this is just kind of a helpful aid and something to look forward to. But if P is true, then Q is true, is functionally the same as not P or Q. In other words, either P is false or Q is true, possibly both. And when we check that, so when P is false, either P is false. In all cases that P is false, rows 3 and 4, we get a true or statement. In all cases where Q is true, which is row 1 and 3, we get a true statement. But when P is true and Q is false, in other words, you look back here, when the left side is false and the right side is false, which is not P, is our left side, so now we can look at this square, not P is false. and Q is false, then we get a false statement, just like our disjunction when both the left and the right side are false. Okay. So that's my introduction for truth tables for you. I hope this helped. Let me know if you have any questions. We can talk about it in class. Read through the chapter. I think that will help a lot. You might have to go back and forth as usual. But that's it for today. And I will see you next time, which will probably be in a few minutes when I record the next video.